served as editor-in-chief for a special issue in the same journal in 2020. So, thank you, sir, for joining today's event. So the session is all yours, sir.
Thank you very much, Dr. Kundu. So, even though professionally I call you Dr. Kundu, but you are like Shurojit to me, like younger brothers. So is Ayan, who is also a faculty member of this institute, whom I know personally. Coming to my lecture, before I go into the details, first let me extend my most sincere thanks to the organizer. Even though it's a virtual event, it takes quite a bit of preparation. In fact, probably on some front, it requires more preparation on the digital because in real time, you can adjust certain things in the spot. But here it's like a digital, either 0 or 1. If there is any kind of issue, you really lost the signal fully. So I extend my thanks to the organizers, the director of the institute, Professor Gavil, whom I know personally. I remember quite a few events. One of them was Indian Antennoid 2012, where Professor Gavil and Professor M.N. Sharma are there as participants and as presenters. And in fact, Sikkim, as for any Bengali, is very close to my heart, and we have visited various times. And in fact, during this pandemic, this North India taking very good initiatives. A few days before, Dr. Toimul organized this energy harvesting Indo-Canadian conference where we had full of speakers from different parts of the world, including Professor Yahya, who is my collaborator, Professor Siddiqui, Professor Nasimuddin. We talked about our energy harvesting and wireless power transfer applications. So thank you very much. Congratulations for organizing this webinar. And as you have mentioned, it's a webinar series, so I sincerely believe it will be continued in a very focused manner, and that would be really beneficial for the young students, researchers, and also some of the faculty members who are at their early career of research. So with this background information, let me start my technical presentation. So I'll now share my screen. So let me know when you see my screen. No. Is it getting loaded?
Yes, sir. It is visible, sir.
Thank you very much. So I'll go to full screen now.
Sure, sir.
Yeah. So this is not my slide. This is the beautiful flyer you people created, and it reminds me the beauty, the natural beauty of Sikkim, the misty hilltop. And there are so many places. Like I really have been quite a few times. In fact, Gangtok, Peling, that are real attraction for, of course, Bengali and also for the world tourists. So today's talk, as already all of you know, I'll be talking on cognitive radio technology, concepts, evolution, and antenna requirement. This is the panoramic view of IIST. We are pretty far in terms of the physical distance, but because of this virtual initiative, distance is not a bar nowadays. And we are really having many such webinars and other kind of activities. So before I go into the details of the today's agenda, let me spend a couple of minutes or so to take you to a virtual tour about my institute and also about the research activities that we do at IIST and also in collaboration with Professor Yahya at Royal Military College of Canada and some of the other collaborators. This is where we belong to. This is normally I show in the international podium. The extreme southern part of the Kerala. IIST started its journey in 2007 with a specific focus of creating quality human resources for Indian space mission, and also IIST is the first space institute in Asia and also one of the unique across the globe catering to the education research and high-end activities, especially catering to the Indian space mission in this particular area. The man behind this institute was Dr. Kalam, the former president, as well as known as Missile Man of India. And it's a proud information for all of us to share that almost 1,000 students of IIST are serving in Indian Space Research Organization in different capacities, I mean, in different positions as scientists, because as per the protocol and as per the norm, our IIST BTech students with a given condition, they join ISRO as Scientist C, and later on they can come back for higher studies for masters and PhDs. And ISRO scientists can also visit us and come for higher education. So, in the next 3 to 4 minutes, I'll be taking you to the virtual tour about our research journey. Sorry. The research activities in my group can be predominantly divided into 3 domains. The printed antenna research, which is pretty close to my heart, and we have started this journey quite a year before. It is almost 1.5 decades now. We have contributed into different areas of printed antennas, ultra-wideband, reconfigurable, multifunctional, SIW-based and dielectric antennas as well. As I mentioned, being a part of Indian space mission, we have very strong rapport and collaboration with various ISRO centers, and we do some joint project which is very much focused towards the space mission. With this type of motivation, we design some feed antenna design for satellite tracking applications. Today is the day where I'll be going into technical part of that. These are for LEO satellite tracking, which is quite a tough and commendable job. We are jointly working on designing the tri-band, KSX and Ka-band antenna for auto tracking kind of applications, where you receive the satellite data as well as you ensure that your ground station data and satellite antenna, ground station and satellite antenna are looking towards each other. And the last leg of the research, which is started just a couple of years before, and then that is basically the millimeter waves and terahertz. Here also, we are establishing our facilities, and in fact, we do some collaboration with, SAC, Space Application Center, Ahmedabad, and some of the other institutes for designing some photoconductive antennas. And this is really costly and cost and time expensive in the sense this requires specific facility, clean room, and stuff like that. So we are growing in this particular direction also. This is a strong area where we have quite a bit contributed. You can probably see some of our contribution in the open literature, which is basically some kind of printed antennas, multifunctional antennas, dual complementary antennas, etc. And then some of these concepts of late have been extended for various applications, starting from the cognitive radio applications and multifunctional applications, on which I'll be coming into the very details very soon. I think there might be some data connectivity issue at my end also, so I see some of my pictures being selected and it's coming a little bit slow. Anyway, so this is a slide which actually shows our collaborative work, some of the outputs with Vikram Sarabhai Space Center and National Institute of Interdisciplinary Science and Technology on different kind of bandwidth reconfigurable antenna and some wideband LP and CP type of antennas for specific applications, which is basically the reusable launch type of applications. So this is not very, I would say this is very new, but it has to, even though existing research, when you say it is for space, you have to do a lot of extra qualification, because normal antenna engineers or normal RF engineers will not consider the quality and specification and testing that is done when your antenna goes to space. So there are a whole lot of other parameters that needs to be tested and needs to be checked when you want to stamp your product as space qualified. So like probably on some other occasion I'll be talking on some of those aspects. So this is some of our contribution on metamaterial inspired antennas and circuits. and I'll probably delete first and go to the main agenda. These are some other kind of contribution on ultra-wideband balanced antipodal tapered slot antenna for cross-polarized radiation. In fact, some of our concepts have been very, very useful, and it has attracted attention from the industry as well as the renowned academicians. And these are some articles recently. All those articles and some of our research has been combined together to come up with a new book with Taylor and Francis. So this is a slide where I'll be going into details today, which is basically showing our activities on cognitive radio antennas, which is IEEE magazine, couple of papers, and then there is a couple of transaction papers on these, and some more work are in pipeline. So I'll be try to covering most of these concepts in quite a detail. And this work, in fact, I'll be showing a nice video to you how some kind of metamaterial inspired concepts, pitching resonators, and the motorized rotation combined together to come up with a multifunctional antennas, which gives versatile applications of frequency tunable notched as well as tunable narrowband application. And as you'll be seeing very soon, that this type of work has real applications for cognitive data. And this has been done extensively quite a few times. We have applied this concept on various types of and done the experiment so many times at my institute. And when I was doing my, completing my PhD, or in, I guess, late 11 or so, we were doing some experiments on certain things. And at Calcutta University, there were certain limitations. So, and then we developed more ideas, and finally we completed a lot of experiments in Royal Military College and then also Queen's University. And also, after I joined IISc in 2013, we have contributed. And that is because of extensive research, extensive experiments on this particular form. And this is a new area of our research, which is on dielectric resonator-based wireless power transfer. A couple of my PhD students are working in this particular area of a near field and far wireless power transfer. And as you know, in this one, we are to buzzwords for the it will be coming in a bit. Many of you have heard me in the other podium and talked on detail on this kind of application. So this is the work that we did in 2018 summer and part of 19 as well on the dielectric resonator based wireless power transfer. And those who are interested in this, you can go into the details of our work. As I mentioned, and that photoconductivity is a ball game. So it's just not antenna, it's antenna and electronics, material science and photonics together. With support from SAT and with some specific vision and also some of the labs, the physics lab across the country with TIFR and the support, and also from ISAT Trivandrum we have done and designed some antennas for such space application. The main fabrication was done at SAT Ahmedabad. They have one of the best clean room, and then we characterize those antennas by embedding some kind of lenses, which are called dielectric lenses, on the antenna, and then some of the characterization was done at ISAT Trivandrum. So this is quick virtual journey about our research activities that has happened over the last 1.5 decade. So these are the some other, probably this is the last slide as far as the journey is concerned. This is a work which is basically a very recent design of tri-band antenna, A6 and Ka-band, with collaboration with National Remote Sensing Center Hyderabad, where a new antenna system will be replacing an existing X-band antenna, which is receiving data from the satellite only at X-band. But because of new payloads and a lot of requirement of sending high throughput data and high dense packed data, we need to receive the data, of course, to transmit as well. So for that, the new idea is to replace antennas which are X-band by simultaneously receiving at A6 and Ka-band. So this is one of the designs where there is a horn for X-band, there is a dielectric load or Ka-band, and 4 S-band dielectric rod, which is arranged in a 2 by 2 array fashion. So with this, I conclude this virtual journey and let me take you to this talk, which I'll be mainly concentrating on the cognitive radio. So these are a couple of slides from very recently held IEEE 5G conferences. I just wanted to give you some information regarding the generations of technology, mobile communication, 1G to 5G, because cognitive radio, MIMO, these are some of the enabling technologies for 5G communication. So when someone is really interested to do know what is cognitive radio, what is its evolution, and how to design certain kind of antennas which are not conventional antennas but little bit intelligent antenna, or some people call it smart antenna. Whatever it is you call, you need to know what is the applications and how it is connected to the modern 1G to 5G communication, especially the 4G and 5G communication. So I'm going a little bit fast because I want to concentrate on the main part of the presentation and I want to take some time. And as I told at the very beginning, there are a few other events also today. So I invite you all of you to attend that one, which will be a panel discussion at starting 5P with Professor Yahya and some of the other experts of the panel. Probably some of you are already having those linked with you. Anyway, so this is a slide which shows the present versus future technologies for as far as the antenna length, antenna frequency range, and available spectrum, maximum data channel, etc. are concerned. This is people talk a lot like about so but what is the basic challenge that we need to understand when you think of 5G? You basically talk about the femtosecond cells, and what you need to have is the high gain antennas, and of course when you talk about the base station type of applications, you have to ensure you cover the entire horizon. So you have to have some kind of beamforming technique or a massive MIMO type of structure, so that you have a pencil beam with a high gain, but at the same time you ensure that entire horizon is covered. And as far as the current 5G band has been considered, because here antennas are linked to this, so I am just showing this information that even though some people think that 5G means we are trying to move at the very higher side of the, so it's not that. Even though spectrum is not yet finalized, but there are certain bands which have been identified that have been touted as best solution for 5G. In fact, you will see that even sub 1 gigahertz band or sub 6 gigahertz band, like as we see 3.3 to 3.8, and so on, are also being touted. But then also we have the millimeter 5G band, which will be probably working. I mean, again, it varies from country to country, from different agencies, different protocols, and so on and so forth. For India, 28 gig and 38 gig and some of the high frequencies are also being considered along with the sub 1 gigahertz and sub 6 gigahertz band. Because I am having a running project with DSP SERB Science and Engineering Research Board of the Cognitive Radio for 5G applications, that's why I thought of sharing some relevant information on this particular direction. So these are some of the basic antennas, but those are configured in a massive MIMO configuration for base station as well as other kind of application. And if you go into the literature, I'm just telling this information at a surface level so that you can combine these concepts later on what I'll be going to talk on detail. So these are different kind of structures there, and as you know, many kind of structure into a probability correlation and different base station as well as other applications. Very recently, one of my students was presenting a paper in a virtual conference at IEEE 5G World Forum, which happened in a couple of weeks before. So I just thought of showing some of the structure there. So we have designed some kind of antennas, which is for 28 and 38 gigahertz applications. And some other designs are for user equipment applications like smartphone or tablet applications. Or you are thinking of having some kind of micro antennas, we have public feed array, and then we place a few more antennas for 28 and 30 gigahertz applications. So together, the placement of the antennas that the other electronics are not disturbed, as we know that antenna engineers, when it comes to the wireless applications, are given the toughest job to adjust the antenna's position, size, etc. And I mean, after everything is done, so after everyone has taken their space, whatever limited space and stuff is available, antenna engineers are asked to adjust in that particular domain. That's why people are probably have to be really smart and to come up and to satisfy their constraint. So this particular part is because I was talking about the MIMO antennas. You need to have some mutual isolation reduction or mutual coupling reduction. So there are pretty few techniques. One of the techniques we have recently reported is to using some kind of VBG structure, and by embedded those kind of VBG structures or different kind of splitting resonators, you can actually reduce the mutual you can actually reduce the mutual coupling for individual antenna elements. So with this very basic information on the 5G, which you can connect later on with the cognitive radio antennas, later come to the cognitive radio part of my talk. So this particular portion that I'll be talking for next half an hour or so is outcome of our extensive work. And if you want to go into the details of this, because as you understand that in 1 hour or so, I can't explain everything, but I hope some of you will be motivated and get some new ideas and indicators. So those who want to go dig and want to, come up with some own work and get the ideas, I'm advising them to go into our articles, which will be mostly available in IEEE Explore, and this particular book on multifunctional ultra-wideband antennas with Taylor and Francis, with myself, Professor Siddiqui, and Professor Yahya. So there is one chapter completely dedicated on cognitive radio antennas in this book, which is chapter number 5. So before I go, this slide is not exactly related to cognitive radio, but if you see the antenna evolution, then it is basically the communication which has driven the antenna engineers to come up with better antennas, high bandwidth antennas, etc. So narrowband to wideband to midband, ultra wideband, etc. has happened, but the problem, or rather not a problem, a statistical information first time which was proposed. You want probably those who you are aware of the growth of this technology, they must be knowing. But for others, it's a surprising fact that one MTech thesis first identified the concept of cognitive radio. What was the concept? The concept was that primary users in a fixed frequency spectrum allocation policy, the spectrums are allocated in a static manner. So when you do the spectrum allocation in a static manner, it is the user's perpetual right to use that spectrum. The survey, different kind of surveys, IEEE survey, a survey done by Professor Rappaport and all, reveals that the primary users are quite a few times idle. So those idle frequency band for certain time are called white space or spectrum hole. So the idea of cognitive radio came from here, something which is like our Airbnb model of the business nowadays. The rooms are being shared with the guests for the secondary users. So similarly, when you have spectrum holes available, which are called white space, those spectrum holes can be allocated to the secondary users. But after ensuring the fact that primary users are not affected. So this kind of application will be requiring a different antenna requirement. So the idea was something like this. You have to identify which are the spectrum holes currently available, and you have to ensure those spectrum holes are properly used, and secondary users can be allocated to the spectrum holes. Thereby, you have a better spectrum utilization and spectrum utilization efficiency, of course. But this is a very nice idea. But how do we really come up with such a situation? Because you need to know where are the spectrum holes available. So where are the white spaces as of now? That is called sensing. So you need to sense, and then you need to ensure that we can communicate at those holes. So this is the basic idea of the cognitive technology, and it will have different applications, of course, because you are utilizing the spectrum in a more effective manner. So you have high data rate, you are using the spectrum in opportunistic way, and many new ideas and new initiatives of government of India like Smart City, Digital India, etc. will be supported with this kind of approach. So I will be going to the journey of CR now, but before that, let me start from the very basic, those who are at the beginners, because as I know, Surajit mentioned me, there will be UG students also here. So you know the ultra band was, declared in 2002 by FCC, the Federal Communication Commission, 3.1 gig to 10.6 gig was given the ultra band. At the same time, it was mentioned that the ultra band should operate below the noise stroke because of some of the existing signals, different kind of narrowband communication already existing. And this ultra band actually evolves from the spectrum signal technique. And in our book, in chapter 1, there is a very nice description and nice flow regarding this ultra band communication. So when you come to this ultra band communication, you need to ensure that you have antennas which are compatible to cover that much of spectrum. So these are some popular antennas to cover those big, ultra band approach. Ultra band, which is FCC ultra band. In fact, there are other better solutions also. Sometimes printed antennas is one of the best solutions. Some people think the dielectric resonator is a good solution, but dielectric resonators, the main issue is it is not, easily, it's not low profile, so you cannot adjust in many of the applications. But there are certain situations where those antennas are also very good and effective. So, as I mentioned, within the UW band, there are some narrow bands like 400 megahertz for WiMAX and 700 megahertz for W band. There are some just representation, but there are other concepts also. So we have to ensure and we have to design antennas which will be covering the ultra band, but not those narrow bands. So some of the recent concepts like ultra band multifunctional antenna, MIMO antennas are coming together to come up with different kind of solutions in communication, in fact, better solutions. So, those who are working in this particular area, is deep into the details of this. In this particular slide, what I want to show is if you compare different kind of capabilities of different IEEE standards and ultra wideband together, then you see wireless LAN, Bluetooth, wireless virtual area network, ultra wideband, etc. If you see that ultra wideband is for low range, short range, and maximum data rate kind of. So with this, I go into now in depth of the cognitive radio. Those who are beginners, so they should know what is the meaning of cognitive or rather cognition. A cognitive system or a cognition means basically it's an intelligent system which can adapt depending on the boundary, depending on the environment, and it updates itself by fetching those information. So in a nutshell, it's basically updation and act, observe and act and then learn. So this is called the cognitive cycle. We call it popularly ODAL, O-D-A-L. So observe, then decide, then act and then learn. Anyway, as I mentioned, Mitola, that in his master's thesis pastime actually indicated this idea of having these spectra modes and then utilizing them efficiently. So if you see the Oxford Dictionary, this is the definition of cognitive, the mental action or process acquiring knowledge and understanding through thought, experience and sense and then adapt and act properly. And this is the definition which is from, as per Professor Hickey, cognitive radio is an intelligent wireless communication system. So obviously, if it is an intelligent, so it will be requiring the intelligent antennas also. So sensing antenna and communicating antenna are the main important prerequisite to establish such a cognitive system. So you will get more information on this from our book, chapter 5. And coming back to the antenna requirement, before I go into some of the work on cognitive radio antennas, you probably should know that the evolution of multifunctional antennas. Some people mixes these multifunctional antenna with a reconfigurable antenna. To make it clear, so reconfigurable antenna can be of different types: the frequency, the pattern, the polarization, and the combination. And when you want to actuate one of these reconfiguration mechanisms, you have to either rely on the electrical or optical or maybe physical or some material change based type of concept. But from one aspect or from a point of view, the multifunctional antenna is also one kind of reconfigurable antenna. But here, instead of going for a particular frequency pattern or polarization, we basically stress on the operation. So the antenna should be operational for different kind of applications. So sometimes it might be operated at a band which will be for UWB, sometimes not UWB, sometimes same antenna has to work as a narrowband antenna. So it's not precisely frequency configurable. Sometimes the gain requirement also be different. So if an antenna can perform various operations and satisfy various functionalities, then I call it a multifunctional antenna. So this is a slide which shows the concepts of the antennas and the cognitive radio. As I mentioned earlier, this is the picture which shows the presence of the spectrum hole, but this is a static frame. And actually, you can imagine that the positions of the holes are getting interchanged with time. So spectrum holes or white spaces are not fixed. So that's why you have to ensure make sure of detecting these holes and then using them for communication. So wideband or ultra band antenna is a prerequisite, and then you can have a tuning arrangement. I mean, some people call it filter integrated antenna also, filter. So this is one way of solutions. And then the approach which was done by initial researchers led by Professor Christodoulou and others for cognitive radio antenna is a basically hybrid approach. What do I mean by hybrid approach? Because we said that we need to have a communicating antenna, a sensing antenna first. So for sensing, you need an ultra-wideband structure. So these antenna can act as an ultra-wideband antenna, which will be basically indicating the decision that which bands are connected. Then some of these antennas has to communicate by actuating a motorized rotation where a motor sits on the backside of the substrate and ensuring that one of these radiators are connected with the feed line, and these radiators resonances and properties are designed accordingly so that at a time one of the radiators will be actuated by the rotational mechanism, and that rotation is executed through a motor which sits on the backside of this substrate. So this is basically a tunable narrowband section. So each of these antennas 1 to n are basically tunable narrowband antennas, but tuning in this case is done by motorized rotation. And to go a little bit more into the details of the meaning of cognitive radio and the spectrum holes, you have to go into the literature. So this is a very nice paper by Professor Christodoulou and his group where they have explained the concept of cognitive radio. Here PU is indicating the primary users, ACU and secondary users. So you see there are some spectrum holes, and these spectrum holes can be allocated to the secondary users, ACU. There is another situation which is called the spectrum underlay scenario where you have primary users, and even though primary users have already occupied some spectrum, you can use the entire spectrum for the secondary users provided you are below certain level. So that is called the allowed interference level. So this is the second scenario which is called spectrum underlay scenario. So in this way, the cognitive radio, whether you go for spectrum overlay or underlay, you need to know the position of the holes, so which requires the sensing antenna, which is wideband sensing or narrowband sensing, and then you have to have multifunctional antennas to actuate such operation. So this is the basic prerequisite to come up with multifunctional antenna, which is the heart of cognitive radio antennas. As I mentioned, you have a sensing ultra-wideband antenna. For our case, as I will be showing very soon, that in fact we did not deploy two pair of antennas. With a single antenna, we have actuated the sensing and the communicating through a mechanism which I am going to explain very soon. So this is not our work, this is the work reported by Professor Christodoulou and some other groups. As I mentioned earlier, you see this is a micro-stiff-fed ultra-wideband elliptical, and it's a quasi-elliptic, I can say, ultra-wideband monopole antenna which acts as the sensing antenna. And you see there are pieces of resonators which are mounted on a circular substrate. And this circular part is actually rotatable, and this rotation actuated, as you can see from this particular picture, there is one motor sitting on the back side, and that motor actually ensures the mechanical actuation or rotation of this particular. Thereby, this is the feed line. At a time, one of the radiators will be connected, and with the feed line, and thereby this antenna will be acting as a frequency reconfigurable narrowband antenna. And there are some other mechanisms like having some integrated filter section, and these filter sections can be made configurable. And this is another idea. As you can see, this particular section is basically the filter section. It's a microstrip printed monopole antenna. And here we have designed it in a way, you see that there are multiple diodes and then some pin diodes as well as some, of course, biasing pattern, etc. will be required. So basic idea is this portion is like acting as a filter. How? So depending on the actuation of the switches and all, sometimes either this path or this path will be activated. And these two paths will be corresponding to different frequency because these are different types of resonators. So thereby these antenna can act as a reconfigurable antenna, rather multifunctional antenna. So this is another similar kind of work, but here the switches are not conventional electronic switches, not pin or varactor, but these switches are basically, in this case, are the optical switches. So because these are optical switches, these are excited by optical beam. It's a little bit complicated arrangement. That's why there are some fibers, and through these fibers, the laser beams are passed through. And then when you activate that particular laser pulse, and then accordingly some of the switches will be activated and so on and so forth, and you get a reconfigured antenna. Now we come to the last wing of the work, the presentation, which will be based on our work. So here, when we started the work around 10 and or maybe a little bit more, we are initially doing some theoretical work for different kind of splitting resonators and applications. So we first came up with an idea of design frequency notched antenna. At that time, we really did not think that this kind of application or extension can be later on even think of. So this is probably those who have followed our work probably know that this is a kind of resonators, splitting resonators which are loaded over here. I know Shurujit and his group also has done quite a good amount of work in a similar kind of technology. So these are the resonators which are loaded on the CPW line. The beauty is it doesn't disturb the radiator, and thereby you get the frequency notches depending on the sizes of the resonators and their frequencies, and you can very nicely design different kind of antennas, not only the circular monopole, other kind of structure also. As we see here, due to the presence of the splitting resonators, you have the frequency notches there, and that can be verified using the surface current distribution concept as well. As you can see at 6.3 GHz, which is the SRR resonance, the antenna is not excited. Whereas the other frequencies like 4 GHz and 8 GHz, the SRR are transparent, the entire signal passes through. So one of the confusions some people are having regarding this mechanism is what exactly happens. What exactly happens is these are very high Q resonator, and if you see the circuit modeling and the equivalent circuit modeling here, actually the resistance or the effective impedance of the resonator is widely varied, not at all 50 ohm, but depending on because these are parallel resonances, the impedance over here goes to something sometimes very low or very high, depending on the type of excitation it happens, either electrical resonance or the magnetic resonance. So what happens is basically it's not absorption or any metamaterial effect, so it's a filtering effect. So at those frequencies, the signals is effectively reflected back, not radiated or in other way, because it is an impedance matching and impedance mismatch. So impedance mismatch basically causes reflection. Of course, a tiny amount of radiation or something like that can take place, but that radiation is not at all effective radiation. So this slide actually explains the performance of this antenna using a very beautiful animation, where you can see the radiation pattern of the antenna with and without the SRR loading. As you can see, when you load the antenna with splitting resonator, at some point, due to the presence of the SRR, the radiation is completely ceased. As you see now that the right-hand side balloon gets completely shrinked, so that is basically indicative of the fact that there is a notch frequency at which the antenna doesn't radiate at all. So these are very straightforward, the radiation pattern at plane and H plane. I'll skip some of these things, and then for such an antenna, you have to ensure that your gain profile is also a notch type of gain profile. Then we extend these concepts with different kind of dual band and etc. So here was the first breakthrough, and from there we got the idea that this antenna has a application for not only frequency notching but also for towards the cognitive review. So if you see this particular table very nicely, which is from our antennas and wireless propagation letters, the same antenna, the radiator is same. This is the top metallization. You have a resonator, splitting resonator, and sometimes you are having the switches over here. So depending on whether these switches are open or short, or depending on whether SRR gaps are closed or not, so you will actually three different antenna responses from a single antenna, named as A, B, C. A is the narrowband configuration. So what happens when the switches are closed is they effectively create some inductance. So this notch filter is converted to a band pass filter, and their combined operation gives the frequency narrowband operation, which is named as configuration A. Whereas in configuration B, when the switches are open, it's basically the frequency notch deltoid band. And when the SRR rings are closed, you get the configuration C at the antenna, again quad 7 ultra-wide band. So this is planar ultra-wide band circular monopole antenna, and it evolves in a way such that it gives three antenna responses. So immediately, this was a kind of breakthrough. First time, if you go dig into the literature, we reported this concept first time in 2015, that a single antenna gives three different responses. And then immediate extension was that the one of the configuration which is not ultra-wide band is good for sensing ultra-wide band sensing, whereas the narrowband is good for communicating antenna. But we have to make the narrowband reconfigurable. Then only we can claim it as a cognitive radio antenna. So immediately we did not come up with the reconfigurable, tunable narrowband operation. So what initially we showed was if the SRR sizes are tuned if you have different SRR sizes, and then depending on their dimension, you'll be activating different resonances, and thereby to ensure that you are having a kind of narrowband reconfiguration. But SRR size changing is okay theoretically, but practically, once you have printed a SRR, you cannot change the size. So later on, we propose some other ideas. Of course, I'll be coming to that part as well. So this was let us wait for a few more minutes for that. So this basically shows if we use different sized SRR, then you basically actually can tune the narrowband operation. So this is the two different configuration. One is the notched operation, and another is the narrowband operation as far as the S11 response is concerned. And this is the realized gain plot of the antenna, and it basically beautifully matches with the idea that I was talking about. So as I mentioned, this was a kind of breakthrough, and we explained some group delay responses as well. Like for one of the configurations, which is full ultra-wideband, as you see, the group delay is completely flat. In another case, notched case, you get quite a bit of delay over here, and this is the verification of our concept from a different perspective using the Poynting vector idea, where you have a filtered energy entering the antenna for one of the cases, or in another case, you basically allow the entire energy to enter the antenna, excepting a narrow band, which is basically the north band. And this idea is so generic and so, in the sense it is so robust, we immediately came up with application of this concept on different kind of radiator. It is not only the monopole, because it is the the resonators are placed into the feed region, so we are not directly disturbing the radiator at all. So it can be applied on any kind of printed antenna. That's what we have established, and we have, if you see the literature, we have reported on Vivaldi type of antenna or anticonductive part slot antenna, on other kind of antennas also. Some of my students, scientists from ISRO Center, they are applying this kind of concept even to get some frequency notched operation from a horn antenna. So this is the uniqueness of the concept. As you have seen probably later on in 2018 and 2017, we have published this concept in IEEE transactions by putting this kind of resonator here or here on the aperture or towards the signal line. And then this particular work is later on extended. I will be going a little bit fast over here by using multiple resonators on the ground plane and embedding them with different sizes, and the switches, as you can see over here, we can actually shift the resonances, and we can get triple band notched or triple narrowband responses. And that this particular part of the experiment was done with manual copper switch, so it was not an actual switch which is supposed to be a pin diodes or RF mains, but then for proof of concept academic experiment and verification, it is okay. So as you can see, this is in-house fab, this is the antenna, these are the resonators with different orientation, and these are the switches, and this is the combined response of the antenna, which depends on some theoretical understanding as well, because these resonators are sub-wavelength resonators, sometimes we call it metametrial resonators. So you need to know how to have their equivalent circuit and the calculation as well. This particular slide, if you follow properly, it summarizes the entire operation. So if you see that at this stage there are no switches over here, I mean the switches are open, and then just concentrate in this particular area. When I close those switches, the antenna response, as you can see on the right side, that earlier we had a frequency notch altered band response, now it's a narrow band response. So in this way, if the switch is toggled on off kind of thing, the same antenna behaves on a two different configuration, frequency notch and narrowband operation. So this is the idea which can be very, very useful for some of the modern radios, including the top limited radio. And for triple notched case, because we have the option to incorporate three pair of switches, and then you can get triple notched response as well as triple narrowband response. So that's what I am showing in this particular slide using the Poynting vector configuration and other configuration. So this is the operation at a glance. So this is NB1, NB2, and NB3. As you can see, NB means it is not narrowband configuration. So here filtered energy at F1, filtered energy at F2, and filtered energy at F3 is entering the antenna. So this length to this length is actually from this point to this point. So as you can see, only a red strip that is Poynting vector. So and this is actually the frequency. So a filtered frequency is only entering the antenna. And then this concept was extended for other kind of antennas, multi-layered slotted monopole antenna, where we use the resonators on two sides, a substrate and superstrate configuration. One pair of resonators are here, and another pair of resonators are on the bottom side. This is all in-house experiment by done. One of my PhD students, Latif, who is currently working at SAC, Space Application Center, Ahmedabad. So these are the fabricated prototypes, extensive experimental and theoretical work, because it involves some equivalent circuit modeling. So this is the equivalent circuit part from the feed line, and this is the equivalent circuit part of the two pair of resonators you can have of the substrate. And this is the first time we experimented with the actual switch, which is in the form of a commercial pin diode. The diodes are embedded on the antenna, because earlier I was showing you the copper switches. Copper switches will not be the exact solution, so you have to have the actual switches, which are pin or MEMS type of switches. And then if you really want to physically change the effective size of the SRR without going for a second trap, you have to have a varactor also. So how to work with the active like pin or varactor, or in some cases RF MEMS also. This part is pretty challenging. We have done that part, and as you can see over here, there are two switches, and these two switches are basically the pin diodes. This is the commercial configuration. Because you are having the diodes, you have to have a bias, which is the DC bias, of course, and then you have a DC for actuating the diodes, and then RF input. So this is bias key, and this is the experimental setup, as you can see, and this is the response of the antenna as expected. When the diodes are on, you get an narrowband response as indicated by the blue line, and when the diodes are off, you get the frequency notch response, as you can see from the black display in the black line, which is actually indicating the. So in a real time, you can actually actuate the switches into different configuration, on off like that, and you can make the antenna tunable. And then this particular work was further extended in a combined reconfiguration, a combined electronic and mechanical reconfiguration. As you can see over here, there is a superstrate which is movable, which can move along the substrate. And this movement is actuated by motorized rotation like this, and through this rack and pinion arrangement. Surprisingly, this part of the work was contributed by one of my BTech students, because there are quite a few UGs present over here, so you can probably get some motivation. That one BTech student, just in 3 to 4 months, he completed this actual work, of course, in combination with one of my senior PhD students. And then this entire antenna was tested by keeping the substrate and activating this movement through a rotorized rotation. So these are the experimental setup. These are the switches which was copper strip, and then later on pin was also loaded. And as you can see, for activating this movement, you need a small motor. So this is a mini motor, a very short, like 10 gram kind of servo motor, and then it is controlled by Arduino microcontroller. So you see the overall configuration. You have the laptop, you have the Arduino, you have the servo motor, and this is the overall antenna part all together. And then that was experimented. And this is the experimental setup. I'll show an interesting video now. So this is the motor, this is the microcontroller, Arduino board. Then this is the summary of the entire operation. You can see you have frequency of short band at F1 F50, and you have narrow band at F1 F50, all actuated through a single antenna by combined concept. So this is a recent design. I am not going into details of this because this is becoming soon. It has not yet come officially. So these are the concepts which have been extended on a Vivaldi antenna by using the varactor diodes over here to embed the varactors. We have to do some kind of modification. So that is also done over here. And then this gives a very beautiful response. The narrowband configuration and reconfiguration, as you can see over here, and narrowband reconfiguration over here, and the frequency notch configuration over here. And this is the measurement setup. This antenna was measured quite a few times at RMC as well as Space Application Center. So I come to the summary part of this talk, and then as you know, there are different kind of diodes required. So you need to know what are the active switches you will be using for your application. So this is a comparison of features wise, consolidated comparison of different kind of pin diodes, arithmetics, and varactors. These points are very, very crucial to determine the switching speed, the power dissipation, the actuation mechanism, etc. So and then later on, parallelly we thought of checking whether we can activate these kind of antennas through some cantilevered beam switching as well. So that work was done, and that particular part, experimental part, still is in progress. So you can actually have a cantilevered beam this kind of mechanism to actuate this reconfiguration. So with this, I come to the conclusion of the talk because I want to take some questions, and these are the acknowledgements and collaborations to my Institute of Course and some IEEE forums and space labs I was talking about. And these are the students who have worked on with me, and this talk is mainly based on our work, apart from the literature survey, which was basically based on Mitola's work and some of the work by Vicky and others. So you can go into the details of the work. I invite you, as I mentioned, I actually was very careful on the timing. Otherwise, normally I take much more time to cover this because I'll be very soon in a panel discussion, which will be starting by another 40 minutes now on. So I invite all of you to come to this All Kerala IPST. Professor Yaya Antar will be there. So if you want to join, you can take a snap of this. This is the meeting number and password in WebEx. And this is the meeting link. I invite all of you to come. So with this, I thank you, but I want to show you the two videos that I told. One is regarding the notched class narrowband configuration using the diode activation. Let me know if you don't see the video, please let me know. If it works fine, then also you let me know.
Yes, sir, it is about to stream.
Yeah. Just follow. This is the experimental stuff. Like as you can see, probably a network analyzer, and this is our antenna I was talking about. And you see the skin of the network analyzer. So the same antenna for different pulses you are applying. Sometimes it is acting as a notched configuration, and sometimes the antenna is acting as a narrowband configuration. So now it is notch, and then next time, because we are giving a digital pulse from source, which is not of course in the part of the video, so probably I can run it once more if some of you have missed. So just see this part. So you see currently it was notch, now it goes to the narrowband configuration. So this is to give at it. I am telling today here because at Queens we did this soldering and all, and the antenna was fabricated in IST. I was there at that time. And we had everything, the chamber also there because our chamber at our institute are in development stage now. So this was the first slide I wanted to, first video I wanted to show you. The second video is this one. This is the student Rajesh. So the video name is Rajesh underscore motor. So you see here the antenna is similar type, but this is a combined reconfiguration mechanical. So you see this is the mechanical movement, and accordingly with the mechanical movement, as you see, the notches are being reconfigured. So notch position is changing from one to another. And then when the switches are actuated, the same notches will be going to the narrowband configuration. So this is the beauty of the work. This is the spin, and this is the actuation in real time. As you can see, this is the rack and pinion arrangement, which is causing the substrate moving, and thereby you get this beautiful real-time frequency tunable notch operation. So with this, I conclude my talk, and once again, I thank you everyone, especially to my very close juniors, Surajit and on Arons and others also, and the management of the institute also. And as I said, I was a little bit fast probably, but I have some time to take your questions and address the queries, and I'll be really, loving to see the campus sometime in the normal situation. Thank you very much.
Thank you, sir, for such a very nice presentation and interesting presentation. It was thoroughly enjoyable, not only for the antenna people, also in our department we are having faculty members from various domain, from VLSI, from devices, from solar systems, from signal processing. So it was really interesting as per the collective feedback. Sir, I would like to take a few questions from the participants as well as from our faculty members, if you kindly allow us.
Please, please go ahead.
Yeah, thank you, sir. So, a few questions I have received. One student have asked that notch creation mechanism, if you could explain it a little bit, the physical reason behind the notch creation of antennas, means how the current elements are getting cancelled out and why it is related with notch creation. That is the confusion there, as per my understanding from the question.
Yeah, so I'll take the question in a generic way first, and then I'll explain the concept that we have applied.
Sure.
So basically, notching means basically you don't want your antenna to radiate at some frequency. Why you need that? Because you need an ultra-wideband antenna, this much, but inside that ultra-wideband at certain frequencies you don't want your antenna to radiate. So that is called frequency notching. So there are different kind of solutions. One of the popular solutions is to create some slots on the antenna or on the ground plane. So those slots will be basically positioned in a way such that it will disturb the current at certain frequencies, and thereby the antenna won't be radiating at those frequencies. So this is the most general and widely used technique till 2010-11. You will see most of the notching technique is like this. So there you are disturbing the radiator, but the principle that I taught based on our work is not to disturb the radiator directly, because we are not creating any slots or any perturbation on the radiator. The idea that we have deployed is basically a couple of resonators, very high Q resonators loaded just beneath the substrate, just beneath the CPW feed line. That's why some people call it filter integrated antenna or filter. So these resonators are designed at some frequency, depending at which frequency you want the notch. So basically these resonators, resonance frequency is the notch frequency. And these are excited by magnetic field of the CPW line. That's why predominantly by magnetic field. So we call them magnetic resonance. So coming to the exact question, the sizes and all, so there are certain calculation, what is the capacitance and what is the inductance of those tiny rings. Those are sub-wavelength resonator. The structure is evolved basically from the metamaterial structure. So some people are very happy to call them metamaterial antenna, which I really don't want to use because it's not a material. But those high Q resonator actually at those particular frequency gives rise to inductance and capacitance, which is around 5 to 6 gigahertz or any other frequency within 3 to 10 gig, where you actually wonder not. The excitation mechanism is predominantly by the magnetic resonance. I hope I have cleared the points.
Yes, sir. Thank you. Prompt answer. Sir, the second question is, what is the effect of different mechanical switches on the total efficiency of the antenna and its related system? Means, as you have shown some different mechanical switching, so will it really affect on the total efficiency of the antenna?
Yeah, so whenever you embed something on the antenna, which is not a radiator, but its purpose is different, definitely there will be some effect. I can't say that there is no effect or zero effect. Some effect will be there. But the beauty of this kind of concept is you see whatever switches, whether it is electrical switches or mechanical actuation, everything is being done on the feed line. And the feed line means you are playing with the signals before it enters to the antenna. So here the impact or the compromise is much less compared to some of the other techniques where we are doing this perturbation directly on the radiator. But definitely, if you say, I can't say that it has no impact. It will have some kind of impact, of course, but it is very, very less, very, very negligible because the antenna aperture remains the same. We are not perturbing the antenna aperture directly.
Okay, thank you, sir. The third question is on a little bit out of the track. Actually, it is not so technical. The question is, what is the way to get an internship at IIST for our students?
So it's a very good question actually. We take interns every year. Only this year, everywhere as it had happened due to the pandemic, we couldn't take this. So what happens is during summer we have a 2 month internship. So typically in the website we advertise the internship in the month of February. So there is a process for shortlisting and etc. Because quite a few applications we get, and then I mean, I am encouraging you to apply. And typically, you will see different topics. By seeing those topics, you can probably identify the faculty members because the direct faculty member's name probably is not given. So you can identify the topics, and then you can identify the area, and then you can apply. So the students from NITs, IITs, other national institutes get the highest preference. In fact, at some point we are not taking students from the private institutes, but now we have opened for them also. But the NIT students or some of the nearby IIT students also come, so they get the highest preference. So that is the mechanism. Summer is 2 months, and winter is also possible for a month. Typically June and July for summer, and mid-December to mid-January for winter. Even though it's not a winter for Kerala, but that we call winter intern as usual, right? So, and before that, of course, you can go through the website advertisement, but you can write offline to the faculty members. Depending in their area, you can see their profile and you can definitely write to them. I also take students like these year. Some students from IIT Palakkad are supposed to come, but COVID has disturbed many things. But some students are still getting some support virtually. Yeah.
So I believe Dr. Chatterjee might have some questions, so he has unmuted. So Ayan, you are free to ask.
Sir, I have a query actually. In the wideband and ultra wideband antennas, specifically at the higher frequencies, the radiation pattern gets degraded. There are many side lobes, and the main lobe is not that much prominent. So, is there any solution to this problem?
Like yeah, because you can't expect a fully identical radiation pattern at such ultra wideband antennas. So some mechanism, I mean, there is no clear cut solution for that. But why? Because if you know the problem, then probably you'll understand. because it is the current. So at high frequency, what happens is you're on the monopole. If you see, the current is not the pure the monopolar type of current. You have more looping of the current. So thereby the pattern kinking will be there. So if you want to apply some kind of concept to get rid of this, but then you have to put some other kind of structures to. But then I don't think it's very easy solution is there. So you have to understand the physics, and you have to. But it is okay, right? Because still for the monopole antenna, still you get the similar type of pattern. You have still the null along the axis of the monopole, and you have the maxima at around 45 degree to 50 degree around with respect to the axis of the monopole. Yeah.
Yeah. Thank you, sir.
Any question from anyone, any other participants? Do you have any more question? You are free to ask if anyone is having any question. So,
Yeah. You can ask.
okay, it is also possible if you later, if you have any question, you could communicate directly to sir, or you may also send me. I can convey the questions to sir to get the proper answer.
Yes, please do that. I'll be very happy to address all the questions, whatever you have. You email it to me. My email probably you have. You get it from Shiroji, and you can write to me. Okay.
Sure. Thank you, sir, for the nice session. So please give a big applause for sir. Thank you, sir, for the session. We are really thankful to you. Thank you, sir.
Thank you very much. Thank you very much. Yeah. Bye.
जरूर चाहिए सर, अब बोलिए हम